For centuries, we've pretty much been told that gravity is governed by this single unchanging number. But what if that's not true? What if that number isn't constant at all? Today, we're diving into a really radical new idea that could rewrite our entire understanding of the universe. And it all starts by factoring in something we all experience every single second: time moving forward. This one question right here is the key that unlocks this entire theory. It's a challenge, really, for us to look at the very foundations of physics and ask, are they as solid as we've always been taught to believe? Okay, so here's how we're going to break this all down. First, we'll look at the crack in our current understanding of physics. Then, we're going to explore a totally new way of thinking about gravity, unlock a mathematical secret that's been hiding in a very familiar equation, and then put it to the test against our own solar system. And finally, we'll see how this all leads to a brand new law of force. Every great scientific revolution really begins with a problem, right? Some little puzzle that just doesn't quite fit. So let's start there. What's the big puzzle that this new theory is trying to solve? From Newton and his famous apple all the way to Einstein's mind-bending warped spacetime, our view of gravity has come a long, long way. But there's a problem, a big one. These theories, they work perfectly in a universe that's just sitting still. But our universe isn't static. It's expanding, constantly. It's kind of like having a perfect map of a city, but the city itself is growing and changing every single day. Our current models for gravity just don't have a good way to account for this constant change, this forward flow of time. So to solve this puzzle of our expanding universe, this theory suggests we need to, pretty much throw out our old map of space and start with a completely new one. And this is where things get really, really interesting. I want you to imagine for a second that space isn't an empty void. Instead, think of it like a vast cosmic ocean. Now picture a planet or a star moving through this ocean. It's not just floating along, it's actually creating a whirlpool, a vortex in the very fabric of spacetime. And that whirlpool, that's gravity. So in this new model, gravity isn't some passive force that's just there. It's an active, dynamic process that's constantly being generated by the movement of objects through space. And this simple shift in how we think about it is what lets us tackle the math in a completely different way. And that brings us to the real aha moment of this whole theory. A moment of discovery found not in some brand new, super complex formula, but hidden inside an equation that a lot of us probably learned way back in high school physics. For hundreds of years, we have treated g, the gravitational constant, as the sacred, unchanging number that you just plug into the equation. But this theory dares to ask a pretty revolutionary question. What if we've been looking at it all wrong? What if g isn't the cause of gravity, but actually the effect? And with just a little bit of algebra, the entire picture flips on its head. You just rearrange the equation to solve for g, and suddenly it's not a universal constant anymore. It's a value that we can actually calculate for any object, based on its own unique properties, its mass, its size, and the speed you need to escape its pull. This quote just nails it perfectly. G is no longer some cosmic mystery that was handed down from on high. It becomes a local property, something that actually emerges from the object itself. It's like gravity, but built from the bottom up. So, what happens when you apply this new way of thinking to all the planets in our solar system? Well, a new and remarkably consistent number for g starts to appear. And this number becomes our new yardstick, our new baseline for testing this whole idea against reality. But hey, a theory is only as good as its evidence, right? So does this new derived constant actually hold up in the real world? It's time to put it to the test, and we can do it right here in our own cosmic backyard. First up, let's look at the rocky inner planets. When we calculate g for Mercury, Venus, Earth, and Mars using their own unique properties, the results are, they're astonishingly similar. They all hover right around that new average we just talked about. This is our first huge piece of evidence that this theory is really onto something. Okay, fine. But what about the gas giants? Jupiter is over 300 times more massive than Earth. This is where the theory should just fall apart, right? Well, it doesn't. Even on this absolutely massive scale, the derived g for Jupiter, Saturn, Uranus, and Neptune stays incredibly consistent. The relationship holds true no matter how big they get. And for the ultimate test, let's look at a real outlier, the tiny, distant dwarf planet Pluto. Even here, way out on the fringes of our solar system, the calculated g fits the pattern perfectly.
This just shows how robust this new relationship is. It holds true across this huge range of sizes and distances. It's pretty incredible.
So we've set up a new way to think about gravity, and we've seen that it works across our entire solar system. So what does this all mean for the fundamental law of gravitational force itself? This is the final and honestly the most important piece of the whole puzzle. So on the left, you see Newton's classic equation. It's served us well for centuries. But when we replace that old assumed g with our new derived g, something amazing happens. The equation transforms, and the constant g just disappears completely. It gets replaced by something we can actually observe and measure, the escape velocity. Gravitational force is no longer some big mystery. It's a direct result of an object's properties. So what's the big takeaway here? We've seen that by just questioning one fundamental assumption, we can uncover a new and, frankly, much more elegant way to understand gravity. This isn't just about a new equation, it's about a new way of doing physics, a future where we don't just accept the rules of the universe, we actually derive them from what we can see and measure. And that really brings us to a final, pretty thrilling thought. We started this whole journey by questioning one of the great constants of science. And it just makes you wonder, right? What other fundamental truths are out there that we've just accepted for centuries, waiting for someone to come along and look at them from a new perspective? What other secrets is the universe just waiting for us to uncover?